Okay, so here's how to do number 9 from the 6.4 work homework. The question says, suppose that 2 joules of work is needed to stretch a spring from its natural length of 30 centimeters to a length of 42 centimeters. Right away, that's important right here. We know that its natural length is 30 centimeters. So that's going to be like the first point, the starting point of the spring. That's where it starts stretching out. From 30 centimeters, that's its natural length. The question, letter A, says how much work is needed to stretch the spring from 35 centimeters to 40 centimeters. So what we have to know is we have to figure out the function. We know that work is equal to a force function, dx, from A to B. And then we know that this force function, when we're talking about a spring, is kx, because that's our force. Force with the spring is kx, where k is your spring constant, effectively like the strength of the spring, and x is the amount of displacement from the spring's natural length. So how much does the spring travel from its natural length? We don't know the spring constant. We don't know this. So what we're given, though, is we're given 2 joules of work. So that right away will give you the hint that you can set this 2 joules is equal to our force function, just our regular force function, kx dx, our standard function, because we don't know what k is. So what we have to do here is we have to find k so that we can find our force function, our spring constant, and we can use that to solve this problem right here, to figure out the work needed if we try to stretch the spring out at a different distance, at a different displacement, from 35 to 40 centimeters. Okay, so we need to know our bounds, our A and B bounds. Let's say right here, so we know that 2 joules of work is needed to stretch it from 30 centimeters to 42 centimeters. But remember, we're not going to write 30 and 42 because that doesn't show the displacement from its natural length. It says that it's going from its natural length of 30 centimeters. So let's say its natural length or starting point is 30 centimeters. And then that spring, so let's say it starts right here. Let me draw a different color. It starts right here, and it's gonna get displaced to right here, where it's gonna get displaced to 42 centimeters. So it's getting displaced this amount. But this is its starting point right here. This is its starting point. So we can instead of 30 to 42, we can really say that this is 0 because it's the starting point. And how much does it get displaced from 0? It gets displayed 12 centimeters. So it's 0 centimeters to 12 centimeters. That's its displacement from its natural length. Key word is just that it's going from its natural length of 30. Okay. We're not going to put 0 and 12 here either, though. We can't put 0 and 12. The reason why is because we have to look at our units. So we're using joules. Joules is the same as Newton meters, Newton-meters. Those are the same units. You see how we're using meters, right? So we're using meters. Right here we have centimeters. So these units are not going to work with what we're given. So we have to change our centimeters to meters. So 0 centimeters is going to be 0 meters as well. But 12 centimeters is going to be 0.12 meters. To go from centimeters to meters, all you do is move the decimal 2 spots to the left. So we're going from 0 to 0.12. So our bounds are going to be 0 to 0.12 meters. Now, me personally, I like to change these into fractions. So I'm going to say 0.12. I just prefer working with fractions instead of decimals. You don't have to do this, but this is what I would do. I would go from 0.12. I would change that to 12 over 100. That's the same thing. Now, if you divide it by 2, you get 6 over 50. Divide it by 2 one more time, you get 3 over 25. So this is 3 over 25 meters. So I'm going to use that instead. So I'm going to go 2 joules. I'm going to start writing joules because we already know the units. We don't have to worry about that right now. We're just going to solve for this. So we have 2 is equal to 0 to 3 over 25. And then we have our unknown kx and dx. We have our unknown kx. we want to solve for k here, right? To find our force function for this spring. So we're just going to solve this integral out. Remember, k is just going to be a constant. So we have 2 is equal to, we're going to integrate. So k, that's just a constant, times x squared over 2. And then this is going to be evaluated from 3 over 25 to 0. Okay. So now it's going to be 2 is equal to k over 2, right? Because that's just a constant. And then we have x squared, and that's going to be evaluated from 3 over 25 to 0. We have 2 is equal to k over 2. Now 3 over 25 squared, you can do that on the side. 3 over 25. If you square that, you square the top, which is 9. You square the bottom, that's 625. So we get 9 over 625 minus 0 squared, which is just 0. So we're left with that. Now we have 2 is equal to 9k over 2 times 625. I can multiply that 2 on both sides. So we get 4 is equal to 9k over 625. Now I can multiply by the reciprocal of this to get rid of the 625 over 9 to separate k. That's going to be 625 over 9. And we're going to get k is equal to 4 times 625 over 9. So k is equal to, and then 4 times 625, that is going to be 2500 over 9. Okay, so we have our k now. We now know our k. So we can say now that our function, our force function, right, when we write an integral, our work is equal to a to b. And instead of k, we now have 2500 over 9 x dx, because that's our k right there. That's k. So we have our work function now. We're now ready to solve for letter A. Okay, so this is how much work is needed to stretch the spring from 35 to 40 centimeters. Okay, so we have to look back at what's our natural length. So again, let me draw a little number line. So we got a number line right here. We want to get from 35 right here. We want to get from 35 centimeters to 40 centimeters, right? But we know our natural length, or our starting point, is 30 centimeters. So just look at how many units away we're from our natural length, right? So our starting point is right here. We're going to start here. We're starting here, and we're going to go like this over here to this end. So we're starting at, you see, plus 5 centimeters of displacement, right? Because this is 0. This is essentially 0 because this is our starting point. So really, this is like 5 centimeters. And then from 35 to 40, that's another 5 displacement. So over here is 10 centimeters. Remember, everything is related to our natural length starting point. So really, we're going from 5 centimeters to 10 centimeters. But again, we have to work with meters because we're working with joules and Newton meters. So you just move the decimal point 2 spots to the left. So it's going to be 0.05 meters to 0.10 meters. So that's going to be our bounds. And now we just solve the integral. So we have work is equal to 0.05. Again, I like fractions better. So what I'm going to do is this 0.05, this is equal to 5 100ths, which is equal to 120th meters. And then that 0.10 is equal to 10 100ths, which is 1/10 of a meter. So I'm going to go from 120 to 110. And matter of fact, I'm going to move out that 2500 over 9 on the left because that's just a constant. And we're allowed to do that with integrals. You can move constants out. So you have 2509 x dx. So work is going to be equal to 2500 over 9 of x squared over 2 evaluated at 1 over 10 to 1 over 20. That 2 I can move out as well. So it's going to be 2500 over, and then that 2 I can move it out here. 9 times 2, 18. At 2500 over 18. And then we're going to evaluate x squared from 1/10 to 1/20. So it's going to be 2500 over 18 of 1/10 squared. So 1/10 squared minus 1/20 squared. So if we do that, 1/10 squared is going to be 1 over 100. 1/20 squared is going to be 1 over 400. So we get 2,500 over 18 of 1/100th minus 1/400. Now to combine that, right, we're gonna do 2,500 over 18 of, I'm gonna multiply the top and the bottom by 4, so we have the same denominator. So we have 400, 4 over 400 minus 1 over 400. So we get 2,500 over 18 times 3 over 400. And now from here, just simplification. So this 3 right here goes into 18 6 times. This 3 goes into 18 6 times. So that turns to a 6, turns to a 1. And then a 10 goes into this one. You see how these have an extra 0? You can get rid of a 0 here. So now, actually you can get rid of another 0 here. So we have 25 over, and then 6 times 4, we have 24. So work is going to be equal to 25 over 24 joules, or newton meters. That's going to be our work for problem A. Okay. Now, for B, it says, how far beyond its natural length will a force of 30 newtons keep the spring stretched? How far beyond its natural length will a force of 30 newtons keep the spring stretched? Remember what F equals kx means. X is the amount of displacement from the spring's natural length. So that's what we're trying to find right now. We're just trying to find X. And we're given a force already. We're given a force of 30 newtons. And we already have K. So all we're going to do is solve for X. So for problem B, we know F is equal to Kx. We know our K, right? Our K was 2,500 over 9. So our K is 2,500 over 9. Our force is 30 newtons. So our force is 30 newtons. And we want to find X, because remember, X with the spring, that X in that equation is just talking about the displacement from its natural length. And that's exactly what it's asking for. How far beyond its natural length will that force keep it stretched? So we're just going to solve for that. So we can plug in 30 is equal to 2,500 over 9x. So to solve, right, there's going to be x is equal to 30 times 9 over 2,500. X is equal to, well, we can take away a 0 here, a 0 here, and now let's see what we can do. We can have a 27 on top over 250. And I think that's actually the most simplified you can get. So remember, we're working with newton meters, and joules. So this is going to be, we're talking about X, we're talking about displacement, so this is going to be in meters, and that's the total displacement.